Welcome, VJ. Nice to see you again. Stuart, nice seeing you again. It's always a pleasure.
After all these years.
Exactly. Glad you made it in town.
Thank you very much.
Yeah. What are you guys here to talk about today?
Well, as you know, I mean, I've been in a submarine for most of my life.
Really?
I've tried to escape twice, right? But unsuccessfully, I'm back in the saddle again. So we'd like to talk about submarine and long haul transmission. I guess we clubbed them together, and one of the things that sort of exercised in our mind is how do we squeeze even more bandwidth out of an optical fibre, and we sort of touched on it in our sort of side conversation before we got in. We've probably milked to death all of the sort of tricks that the free space guys came up with over the years, both in terms of modulation formats recently and prior to that, forward error correction. Mm-hmm. So I think we're facing a straight choice now between more fibres, right, multi-core fibre, probably unlikely, but just more fibres, or higher bandwidth repeaters, and I guess that's one of the things that we're keen on. And I guess the other thing that we should touch on today really is the sort of DCN to DCN thing, which is driving our business at the moment, and how we get the reliability up on the overall system once you've got this virtual fibre all the way from DCN to DCN. So there's two land points, and as well as a submarine section.
Now, we learned a long time ago that a conventional ring across the oceans just doesn't work, or at least it's prone to error, because you're going to have a long outage or long repair cycle when you do have a problem. So if you have a ring environment and you lose one of them due to trenching or whatever the case may be, an anchor rips it up or natural disaster, it's usually weeks or even months before you can repair it. Now, at that time, you're in simplex mode. So what we did 10 years ago was tear those rings apart and create singular paths across the ocean, both oceans. Now we have 7-way diversity across Pacific and the Atlantic, and when a path breaks, we spread that traffic around on the existing links that are still working. And it supports multiple failures at the same time. When you do have a natural disaster, this can be detrimental to an entire coast in some cases, and we're able to spread that traffic around. It's worked really, really well. I think that's something that the folks building them today are going to have to take note of, or maybe they'll learn the hard way. I don't know.
Well, I think you're right. I mean, if you look at traditional older networks, I mean, it's NFL city to NFL city. Whether it's an NFL city in Europe, or which we now have, of course, or in the US. And that's where voice was concentrated, obviously, so it's a natural thing. Now, so all of that route diversity and resilience now has gone away, because you've now got these large data centres sort of dotted around the world, often in cold countries, of course, for expediency. And they've got to now build out that resiliency again. The thing that that I find interesting is that we're now we've gone back to the future in some respects. I mean, back 30 years ago when we had the electrical cross connects and things like that, people bought the cross connect from supplier A, they bought the cable from cable manufacturer B, they might have bought transmission equipment from another party and things like that, and then they put it all together. And what we're seeing now is this sort of disaggregation, of course, where again, the switch is going back into the data center, the transponders are at the data center, and it's just a 1R system from end to end.
Right.
And of course, that then enables people to disaggregate the network again. So you can buy the switch from the former electrical cross connect from company A, the transmission or transponders from company B. Then if you've got an optical gateway close to the beach or something like that, you can sort of take everything back, right, and then procure the system independently. It's not quite as, it sounds very easy on paper, doesn't it? Because the line design of the submarine bit is not trivial, and will, even with coherent technology, it will still be. It
would be trivial if you were satisfied with the amount of capacity you used to use, right? But everybody comes to you and says, no, I want more capacity on that same fiber.
The other thing that's occupied our mind at the moment is how to get even more bandwidth out of the fibre, which you've just touched on there. And we're pretty close to sort of Shannon's limit, I guess. So unless somebody can find a way of getting around that, which I doubt, we are confronting this sort of choice of more fibres, more cables. So you get your network resilience from more cables. That's one, or broader band repeaters, and that's one area where I think it's been a long, slow burn for Xtera with its Raman technology and things like that. But at long last, we've now started to see the potential of Raman.
Sure.
Right. An increase in the bandwidth, and we've. You're probably aware that we introduced a Raman-based repeater 2 years ago. We've got it under the water. It's been under the water on a couple of systems successfully for a couple of years now. But really that was just a starter, right? Because we just wanted to sort of test the principle, not make too many claims about how far we could go in terms of bandwidth terms, but we're now at around sort of 70 nanometers commercially. We can see an easy route to 100. It becomes a struggle then.
Yeah.
Right. Beyond that,
one thing, as you probably know, is Xtera here in Allen. Actually, we developed a 100 nanometer amplifier for the first time, and it's sort of getting that technology into the repeater with distributed Raman and hybrid Raman amplifiers.
In my opinion, it makes perfect sense, right? Because you've already got you're using more of a conventional fiber, and the bandwidth is available on the fiber itself. It's exploiting that capability, and the losses are reasonable at those wavelengths. You're using traditional amplifier types as well, not traditional from a Raman perspective, but something you didn't have to go invent in order to take advantage of. I mean, it makes a perfect build to me, in my opinion, taking advantage of that first. Now, whether that's going to solve all the problem, I'm not so sure, right? People are always asking for what comes next, and I mean, my thoughts on that is more fiber. and the reason I say that is because it's, again, an engineering problem, not a science problem.
Yep.
If we say, no, we're going to do few mode field fibers or multi-core fibers or something that creates even more of a niche, then that makes the cost go up, and it creates an entire ecosystem that isn't there. The equipment doesn't exist, the fiber doesn't necessarily exist, the cabling doesn't exist.
Reliability.
And then I need to splice that and fix it. Where, I could just put another couple of fibers. That seems like a really smart answer to me. I can tell you that's what we're doing on the terrestrial side.
When fibre optics came along, and I was privileged enough, as you know, to be sort of in Harlow, right, sort of working on some of the early fibres myself. The whole world was pushing for optical fibre. So all the big labs in Japan, Bell Labs, and a number of labs in the US, all the fibre manufacturers were investing millions of dollars. In the technology.
Hundreds of millions of dollars,
billions of dollars, which meant a lot in those days, of course. Right, and now you've got niche players sort of trying to get the sort of momentum that these big fibre guys could do, because they've got the weights of governments behind them, and that So I never doubt the enterprise and the industriousness of the human race, because normally given a sort of a scientific problem, we solve it eventually. Like coherent, I mean, that was also sort of prevalent when I was in the labs in Harlow as well. So
it's a groundbreaking one, and again, it was PMD was this awful problem. We just can't get around it. We struggled. We went and measured every fiber. Coherent systems come around and the problem just goes away. Wider bandwidth. How are we ever going to go back and change that fixed filter? Oh, that's impossible. Oh, we got a local oscillator now. This is really good.
I know. You just have to cast your mind back to all those things.
Yeah, and it was.
I remember with PMD, we actually went into the cable factory Christmas Day, or the day after Christmas Day, because none of the machinery was working, and we laid out a kilometre of fibre around the factory, more or less all in a straight line, to measure the fibre, PMD, which is the only way of measuring it.
Yeah.
Right, because when it was on the spool, you get all the
Right.
Yeah,
You need a straight line test, or at least the
straight line
the
with
measurements are different.
with no fiber laying across fiber.
Yeah.
That's right.
Yeah, it's really again, I'm with you. I think if we were out of other solutions, if we didn't have more bandwidth to work with inside of the existing fiber, if putting more fiber into that cable was not an option, and I know there's limits on the ocean portion with powering and such, but it's more of a, well, why don't we go solve the power problem, make more efficient amplification or repeaters, add better power at the endpoints, perhaps a bigger strength member in there to carry it, or somehow solve that one. I think we'd be better off because in the terrestrial part of the world, it's standards. G.652 is still good stuff. We use it everywhere.
We're back to it. We're back to it. Because in terms of Raman efficiency, of course, it's spot on.
It's really good, isn't it? Well, I think we got it right the first time. We should have just stuck with it instead of trying all the crazy. Oh, let's lower the dispersion. No, let's make it median dispersion. Niche applications, large effective area. Again, solves one problem. Nonlinear effects are better, but
it's not so good for
Raman. If I
Raman.
wanted a Raman amplifier, and then you get back to, then what are the products built for? Because that's the other problem. Let's say that you do solve the fiber. For whatever, you got some breakthrough. The university somewhere comes up with a new solution, and it's really easy to manufacture. I don't think that's going to happen. But let's say it did. There's no equipment to go on it. And even if you did make equipment, then your market opportunity is relatively small. Where if you build something that works on standard fiber, your market opportunity is global. It's everywhere. And we use the same stuff today for those cross-country links that you would in submarine cables and vice versa. You have higher volumes, more investment, consequently better pricing. Where if you look at today, every new development or product that's manufactured is built for that fiber type because it's ubiquitous. It's everywhere. It's terrestrial, it's access, it's submarine, it stretches the globe. And you build a product for that, you've got a market to sell into. You build something that goes into a few mode field fibers today and you don't have a market opportunity, and therefore you don't have a business case, and therefore you're going to struggle for funding.